speaker. We have Jenkins, who I've been working with for a while, starting with the Google Summer of Code. I've always been impressed with Lewis's work. Recently, he's been working on Chapel Graph Library, building on previous work on hypergraph libraries. I think graphs and graph analysis are an important tool that can be used to study a lot of different domains. So let's see what Lewis has to say.
Hey everyone, so welcome to my talk on the Chapel Graph Library, or CGL. So the core topic of this talk is on adapting the hypergraph library to use with graphs by making them too uniform. So I explore the implementation of hypergraphs, graph algorithms within Chapel. Yeah, I'm on the blank right now too. So this talk is about CHGL and CAL, the Chapel Aggregation Library, which helps support fine-grained communication, and how to apply both of them to get good, efficient graphs, making them too uniform. So it's also an exploration of how much of the Chapel HyperGraph Library can be reused. So we also explore whether or not we can reuse CHGL in its entirety, and also we analyze the performance to overheads of adding subtraction. And also as well, we definitely go over quite a few Chapel performance issues as well. So in this schedule, I will be discussing the Chapel HyperGraph Library, giving some background on it, the Chapel Aggregation Library, giving background on that, the effort for making global view distributed data structures, and in particular, exploring implementing graphs as two uniform hypergraphs, which are hypergraphs where hyperedges are just sets of two vertices. And we also implement this triangle counting benchmark and analyze the performance and compare it to UBC++, another popular PGAS library for C++, which is entirely fundamentally different from Chapel. And so the Chapel HyperGraph Library is one of the few packages that specifically target hypergraphs, and I believe it is the only package that targets hypergraphs in Chapel at least. It is a dual hypergraph where vertices and edges both have sets that contain each other. So vertices have the set of hyperedges that they are incident in, and hyperedges have the set of vertices that are incident in it. And we also provide some hypergraph metrics, some hypergraph generation algorithms such as Chung-Lu, Euler-Strange, block 2 level Euler-Strange. We have algorithms like S-logs, S-connected components, S breadth first searches, et cetera, It's also meant to be generic and very high level. So what is a global view distributed data structure? So you can think of it kind of like a Chapel distributed array where you can, say, access it from multiple locales without having to worry about, say, processing your current task's index or have to really worry about locality at all. It's all kind of handled for you. And the way this is actually implemented is that each locale constructs a class instance or a clone of a class instance that is local to the compute node. These class instances are stored in the privatization table, and they're given an offset, which is shared across each locale. And this offset is called the privatization ID, or the PID. So it's not to be confused with the process ID, but yeah. And we also wrap this PID as well as a type into a record, and we make use of the Chapel forwarding mechanism, which is going to forward. So basically, it allows you to treat the forwarded privatized instance as So it allows you to treat the record as the privatized instance itself. And so, as I mentioned, it offers high-level semantics, high-level, it abstracts locality for you. It's very, very, very high level. In this example, we have kind of a simple Irregular algorithm where we iterate over set of vertices, set of edges, and we flip a coin to determine whether or not we add an inclusion to it. And one thing to really note here is the fact that this hypergraph rather, is distributed. It's cyclic. The vertices are cyclically distributed. The edges are block distributed, and the for all is also going to be distributed. And we have all these different, say, interesting, very high level, interesting, kind of shared memory looking kind of code, which just seems to work really well and without excess communication in Chapel. Also, kind of to throw in, the HyperGraph library also is now a property hypergraph, where the property map itself is going to be global view, and you can basically pass in that property map in place of the number of vertices, and it handles, say, updating it for you, et cetera, et cetera. And now, so while I was developing Chapel HyperGraph Library, one common issue I've kind of run into was that fine-grained operations, of course, are extremely slow. So I implemented the Chapel Aggregation Library, which in essence can be simplified to collecting individual units of data to be sent in batch. It's overly simplified, I would say, but hopefully gets this point across. And once those buffers are full, so once you have all the data, once you have, say, a full buffer of individual units of data, they can be sent to the locale by just migrating to it via an OR statement and just accessing it via lexical scope. And here, I want to show how the global view data structures all work together. And in this case, there are 3 global view data structures. So I count Chapel's distributed arrays as also a global view distributed data structure. So in this case, we're computing a histogram for vertex degree distribution, right? So again, the point I'm trying to make here is that, like Chapel's arrays, they're very high level. The aggregator currently requires, the aggregator's API is still kind of ugly, so that's why the buffer has to be returned, you can check for, et cetera. But overall, it's meant to highlight just how high level it is. And so what's next? So you can see that they work together. This is scalable code. What's next? Composition, creating distributed data structures from other distributed data structures. So we have a 2 uniform hypergraph, which we are going to be calling the graph. And as I mentioned before, we have hyperedges, which just have which are restricted to 2 vertices. And due to its nature, due to the fact that the hypergraph is a dual, it has to be a static graph, unfortunately, which means you have to know the edges in advance. We use an atomic counter along with aggregation to efficiently claim edges, and we also maintain a cache of adjacency lists, which has significantly improved things by like at least 2 orders of magnitude, which is pretty cool. So the reason why we have a cache is because in the hypergraph, so let's say you wanted to find, say, your neighbors for a vertex, you would have to walk from the vertex to the hyperedge to other vertices, and instead with the cache, just have a constant lookup. So we demo triangle counting, and to be as fair as possible, to measure how much overhead there is, I implement a minimal, I implement a minimal, is that 10 minutes left or 10 minutes in general? Oh.
It's the same.
Oh. Okay, so why triangle counting is it? Yeah, so I chose triangle counting because it's simple enough to be implemented just with distributed arrays. The minimal implementation is bare bones. So as you can see, they're both literally the same lines of code, 6 lines. And this is rather important for performance reasons. So I make use of some locality checks. So it turns out that when you make an implicit copy of an array, the domain is shared with the original array, even if it's remote. So I make sure to make a copy of it, which has definitely sped up things. I only very recently figured out, or rather learned, thanks to Peter's talk on Spark, what's it called? On stencils, right? That apparently local block is now ignored. So I've done most of my performance on release 1.19, but that's been sad to see in here. So unfortunately, this is actually something which seems extremely weird, is that, first things first, there are 2 things that can be observed. So we're compiling with local, which does away with all locality checks. We can see that it is about an order of magnitude faster than it's faster than with locality checks, which is --no--local. And as well, so in both of them, we see this plateau, and I did some investigation as to why. So I would definitely like to possibly get this addressed, say like tomorrow during the coding day. So I did some perf on it. So for one thread, we see that the intersection size takes up 95%. So 91% of the computation time, which is good. But for 2 threads, I noticed that a lot of the time is actually spent in the Q thread testing layer, at least 30% actually. There's more below, And so I skipped forward to 44 threads, and I have no idea what that mem copy is. But the point is that there is some kind of, there's something kind of lower level going on, and that impedes scalability. But also interesting, depending on the kind of graph chosen. So for this case, so I have a real graph. The other one was synthetic, it was a graph 500, generated graph. This is based on live journal, and we get some scalability, but as you can see, it's nowhere near as well as in UPC++. And finally, this lack of scalability in shared memory definitely can be seen in the lack of scalability and not lack of scalability, but the performance in distributed memory as well. But the takeaway here that can be seen as well, the positive, I suppose, is that
I'm sorry, just realized something.
The graph, the T-uniform graph is about as fast as the bare bones version, which is good. There is unfortunately a peak at 2 locales. I've seen this many times before. It's actually visible in the parent here in the graph 500 one, except it's just the fact that the overhead is likely some constant and is relatively small compared to everything else. But overall, it does scale well at 60 nodes. So also as an advertisement, I'm not sure how much time left.
Hi.
Okay, cool. Good. And so I plan to release a Irregular Toolkit soon, full of globally distributed data structures in case people were interested. Cal has, even though it was announced a year ago, unfortunately it has not been cleared to be in its own repository yet. So the works in process of motion to have multiple different things in there, such as a word queue abstraction, explicit termination section that's separate from, say, Chapel sync constructs, and that allows you to wait on like whatever the user wants, basically. So yeah, so this case, so here we have a basic distributed global view breadth first search with the Jenkins HyperGraph, which I thought was pretty cool. And in conclusion, building specialized graphs on top of hypergraphs isn't a bad idea. It's not a bad idea. It's some overhead, but honestly, compared to everything else, it's relatively insignificant. It enables a lot of code reuse, so it makes it possible to create like say a global view distributed property graph from a global view distributed property hypergraph. And this composition of data, this distributed data structure works exceptionally well. There's some overhead as shown, but yeah, but again, it's not as bad as you would think. Both of them use the aggregator and so on and so forth. So I will be definitely missing the local blocks until everything else gets kind of fixed and we can get the local modifiers and all that kind of stuff, which Brad mentioned will happen eventually. How soon? Also, I believe this bottleneck could be an issue with the tasking layer and the fact that it's yielding so often to the point where it's like even if you have two tasks, and you don't have anything else, just yeah. So I have extra time. I actually have the C++ version just to show like how kind of complicated it is compared to Chapel's, but I mean, yeah. I just walk through it quickly. It's in C++. There's no global view programming. You have to do local index calculations, which is of course a pain. But some positives that the synchronous communication, the ability to explicitly make something asynchronous is actually really cool, and I really hope that that feature is eventually available in Chapel. First class functions, I've asked for this since like 2017, but most of it comes from C++. The law comes from C++ anyway, so I guess it's not really fair to compare it, but it is something that is used heavily in the code. And this is like, I guess, maybe kind of a bad thing, I guess. You can get wait for everything to finish, and you have explicit reduction stuff. But that is all. There you go.
So when you're distributing graphs like this, it matters a lot how you're doing the partitioning. So how are you partitioning the graphs?
What do you mean by partitioning?
Is this done on distributed memory?
So it's controlled by the parameter. Right there. So I probably didn't highlight. I probably didn't highlight it appropriately, but it's defined by the user. The user defines the distribution of both.
Okay, so there's a distribution of the vertices and the edges.
Mm-hmm.
And it's not using any kind of a graph partitioner. It's just doing some kind of cyclic or block distribution.
It's just using Chapel's built-in functionality.
Okay.
Related to that, is there an assumption in these graphs? So I mean, some graphs are easy to spatially decompose because like if they represent a physical system, then you can have entire subgraphs kind of mapped locally to the same locales, and that's good. other graphs, like social graphs, there isn't sort of a natural, or at least not obvious what the natural partitioning is. Is there an assumption in this library that you're going to be doing more of the latter style of graphs where it's hard to sort of do a distribution that will sort of maximize locality in the graph sense? Thanks.
Can I defer this question to Marcin?
Graph partitioning is something that we would consider, and the library technically would allow this. Perhaps because we are going to Chapel domains, we would have to consider how to squeeze it into Chapel domains if the partitioning is not equal between locales, so to say. But we haven't really experimented much with it, and for triangle counting, it can actually make a big difference, right? Or for especially for other algorithms like BFS or anything like that, it can make a big difference. But for now, we've been kind of concentrating on the basics. But I see graph partitioning as an application, basically.
And then what kind of graphs are you typically working with? Are they the ones that come from some kind of physical modeling, or are they like social networking graphs, or a combination?
We currently will be using graphs from graphchallenge.org. We've had Graph 500 generated graphs, and we use some other data sets that we were able to download from the public repositories, but most of them were some kind of a social network or whatever is in graph. There's some image graphs in the graph challenge data set as well, so those are more local. Yeah, we've been using kind of all kinds of different graphs. That's what I can say. We haven't really concentrated on a specific kind of a graph at this point, but we haven't also really gone into optimizing our algorithm and partitioning and stuff like that.
But with a hypergraph, if you define it like this, you know for certain, suppose you need to update the graph many times, then you know for certain, or there's a very high chance that the edge and the vertex are in different locales, right? You need to. So wouldn't it be much better to just have one representation and switch to the other if you need it, or for example, have you considered sparse matrix?
For a sparse matrix, so to answer why I didn't choose sparse matrix kind of representation is because there isn't, from what I can tell, a decent distributed sparse linear algebra library. In fact, it's one of the cool summer code projects that's being done this summer. For the earlier question, why not do it? Why use some other representation? More, I believe, for generality. Marcin was actually the one to pick a dual form. Maybe you could explain.
So there are different possible representations of hypergraph, right about that. But because we are storing in such a way, it's easier to find intersections, for example, between edges by going through the vertices. So in a way, you can think of this as kind of so we want to be able to take an edge and find its neighbors, right? So by having this other direction of the storage, we're able to do it easily. Otherwise, it would be difficult and would require some linear scanning.
But I guess this is useful if you just read the graph, but if you need to update the graph, then yeah, it sounds to me that you're always, you're almost guaranteed to have non-optimal locality. Is that correct?
That's possible, yeah, that's correct.
Okay.
Yeah, and in general, it would be very hard to close to impossible to have locality between the edges and vertices.
Yeah, well, if you